Good morning, and thank you very much, David, for that kind introduction. It's a real pleasure to be here today. I've known colleagues at LSE and at Winton for a number of years, and I guess maybe the most exciting thing is just, as David was saying earlier in his introduction, the amount of data that one needs to take into consideration these days when formulating effects on markets and other aspects of mathematical finance are just amazingly outstanding and growing sort of from year to year. Now, it turns out that most of these types of data exhibit one form or another of network effects. So my talk is going to be a little bit different from the ones that you'll see over the next couple of days, in the sense that I'm going to focus very concretely on this aspect of the problem. So how do we make sense of networks? Before kind of diving into that, let me just quickly say that we will be having another workshop on big data, the third in an annual series, coming up at the end of June. It'll be held at UCL. And we've had participation from some of you in this room in previous years. And of course, I would welcome back everyone once again. The focuses this time around are going to be on the sort of usual suspects, the first couple of bullets, but also some interesting things like privacy-preserving inference, which is becoming of greater and greater interest to the scientific and commercial communities. So anyway, please consider the opportunity to come and join us. We still have plenty of poster slots and some speaking slots left. If you're interested, just get in touch with me at any point, and I'm happy to help facilitate that. So as I was saying, the main question that I've been interested in over the last few years is quite simply, how do we make sense of network data? So how do we draw conclusions both from and about networks? And you'll see here I've taken a figure. This figure is actually taken from an IMF report that was published after the global financial crisis of 2007, 2008. And it shows, as indicated, the global banking network with the size of the nodes in this network being related to the proportion of a country's economy that's dependent on the banking sector. Now, what the IMF was interested in this case was a kind of stability assessment. So if you think about things like financial contagion, it would obviously be important to understand when a problem, a crisis in one country's banking system can become systemic, when it can infect the entire global banking system. Now, what's interesting about this is that the authors of this report, in a long technical appendix, indicate that they've tried many approaches to analyze this global interbank lending and economic network, and that they really, at the end of the day, aren't quite sure what to do. Okay? So they came up with a number of heuristics, and eventually they decided that the importance of a country-specific banking sector to the global banking network is some kind of ad hoc combination of the size of that sector of the economy and its interconnectedness. And so the reason I want to kind of make this point very early in the talk is just that it's clear that there's a huge disconnect between what we need, or at least what we would like to be able to understand about networks, and what we actually do understand, which at this point is still not very much. And what I mean is that there's no sort of undergraduate text that you can pick up and sort of take all of the classic statistical inferential methods and sort of apply them to networks and get a sensible answer. Most of that theory just doesn't exist. So the focus of my research for the past few years has been to work at exactly this area, to kind of help to build a coherent mathematical framework for understanding networks. And David alluded to the couple of things that I've been doing in this regard, but probably the thing to understand is just that there are really three key ingredients that will eventually yield such a framework. And this is certainly isn't an effort that's down to a single individual or a single research group. And it's not an effort that's going to be successful in 2 to 3 years. This is probably 5 to 15 years, I would say. So 3 things are required. The first we have in spades, and that's networks that generate data. The theory of random graphs was completely abstract in the 1950s and 1960s when Paul Erdős and others started working on it. But these days, from Facebook to global transport networks to pretty much everything else you can think of, we have examples of mechanisms that generate network data in spades. Okay, the other 2 are a little bit harder to come by, and they take some more work on the part of us, the research community. So first of all, structure. I'm talking here about mathematical structure, the kind of overarching superstructure of mathematics that helps to facilitate analysis. So how do we make sense of a network as a mathematical object? And then ideally from this structure should flow tools, algorithmic tools, inferential tools, decision-making tools that can be understood in the context of this structure. And tools that can be understood leads immediately to algorithms with provable properties. And these, of course, are necessary whenever we want to take important decisions on the basis of any kind of observed data. So as I said, the gap here is that if all of this were mature, we would have an undergraduate level basic textbook that you could pick up off the shelf and implement a whole stock variety of ideas, and they would all have theorems associated with them. Right now, we have a lot of ad hoc and heuristic methods, and our theoretical understanding of what's happening is really sort of racing to catch up. Okay, so that's sort of the context for what I'm going to be talking about. Now, I'll start with these 3 pictures. They may not look like networks in the sense of the last blue blob that I showed you, but they're just representations of networks as matrices, and these are a little bit easier to handle as the networks themselves get larger and larger. So these are all examples of what are called adjacency matrices. And what I've done in each case is I've articulated an ordering of the nodes in the network. I've reflected that ordering as rows and columns of a matrix, and then I've simply filled in the ijth entry of the matrix according to whether or not node I is linked to node j. Now here I've pixelated this by taking linked nodes and coloring them in with black pixels and leaving unlinked nodes with white pixels. So you can sort of visually see some of the structure in these data sets. Now, all 3 of these are actual data sets. The first of these is from the very early days of Facebook, when it was limited to a relatively small number of undergraduate institutions. This is an example from Caltech, and it turns out here that this block diagonal structure you see is apparent because I've ordered the nodes in this network of people that are friends on Facebook at Caltech according to their undergraduate hall of residence, so their dormitory. And this is entirely unsurprising. What you see is that the likelihood of being connected, given that you're in this data set at Caltech, is associated with a boost when 2 individuals in question are living in the same hall of residence. And if we were to reorder this by subject of study or year in school or whatever, you would see similar effects. The middle example is slightly different. It's a network of scientific collaborators taken from co-authorship of papers. And here I've ordered it differently. I've taken the kind of the most collaborative individuals, those with the largest number of connections, all the way down to those with the fewest. The cliques that you see along the diagonal here are sort of the kind of large groups of authors that you get in areas like experimental physics, where it might take 20 to 25 to even more people to complete a paper. So that's the sort of the small blocky structure that you see on the diagonal. And lastly here, you see something that kind of interpolates between these 2. So there are differences in connectivity, but also there's a pretty clear block structure here. So this is taken from a student survey of high school friendships, self-reported friendships in high school. And the nice thing about this study is it did collect a lot of other information. In the particular high school in question, so this is ages basically 14 to 18 in the US system, this school happens to be about 80% white, about 10 or so % black, and another 10% or so not, other category are not reporting. And so again, the block structure that you see here than happens to be by reported race in this example. And if I were to rearrange it by year in school or something like this, you would see similar blocky effects. Right? So clearly the structure of these types of networks reveals information, but the question, of course, is how to make sense of it. So one place to start from a probability and statistics perspective is to think of the links in a network like this as coin tosses. Think of them as random variables, right? And then, of course, the whole kind of modeling interest lies in understanding how to kind of couple all these tosses. A coupled model for coin tosses is a generative model for matrices like these, and therefore is a model for a network. And then the only question, of course, is, well, how do we come up with good, effective models that describe the data that we see in practice? And that's where things get, of course, more exciting and challenging. So now I'm going to talk for the rest of the hour about the following concrete question. When we think about models for networks, how should these models become more complex as the size of the network scales? Okay, so let me give you an example. When you purchase something on Amazon and get recommendations for new purchases, what's happening there is Amazon is analyzing a network between its customers and the items that they've purchased. So this happens to be a bipartite network because there are two types of nodes, but it's a network nevertheless. So when Amazon sort of does customer segmentation to recommend new products to you, that is pretty much the same as saying that everybody who's an Amazon customer can be segmented into a relatively small number of buckets. And then these buckets, you borrow strength within a bucket to cross-recommend purchases, to people who Amazon has decided based on your past history are like you. So that would imply, for example, that, if all of Amazon's customer base can be segmented into 8 basic purchasing categories, then that's a pretty simple model. Even as Amazon grows and grows in its number of customers, we still might only have 8 customer segments. So as a contrasting example, think about something like Facebook. Like, it's probably not reasonable to assume that everyone on Facebook somehow behaves according to, one of 8 groups. But maybe if there are n people on Facebook, maybe we need something like log n groups to account for the behavior of these n people. Or maybe we need as many as square root of n groups or something like that. So that's a quantitative, concrete question that can be asked, and it turns out answered in the context of these types of models. And you can see already here why I'm implicitly focusing on large networks. These kind of questions are inherently asymptotic, and, just like a histogram only really makes sense when you collect a large number of samples, so does this question only really snap into focus as we think about networks that are relatively large, not sort of, the kind of thing you see on CSI where it's, 5 criminals and you're trying to work out how they interact with each other. So to that end, I'm gonna pick up a few key assumptions. I've talked about the first of these. The second is the idea that in the real world, we tend to see relatively few connections, out of the many that are possible. So in particular, there are n of us sitting in this room. Many of us have connections to one another, and yet there are probably nowhere near to sort of n squared connections between us. Whereas if all of us were indeed connected to every other person in this room, then we would have exactly n choose 2 connections, and our graph would be complete, and the matrices I showed you on the last page would be entirely black, right? So when we let n go to infinity, in some sense, we are obligated to let the probability of an edge forming between any 2 nodes in the network go to 0 at some rate. Otherwise, the expected number of edges is going to scale like n squared. And we just sort of agreed that that's probably not very realistic. Now, the last one of these is the one that's perhaps most intricate and subtle and connects most strongly to probability, which I'll be telling you about in a little bit. And the idea here is that oftentimes when we observe networks, so for example, the 3 that I showed you here, when I described how these networks behave, I articulated to you the ordering that I gave to the nodes. right? But many times this isn't possible. Many times we observe a network. Here's a network of cross-references between blogs, political blogs, in the 2004 US presidential election. Now, in this case, the authors were able to work out whether the blogs were left-leaning or right-leaning or more centrist. But in many cases, we would be given data like this without necessarily any or all of the knowledge corresponding to what I would say is covariate information about the nodes in the network. So without node-lone labels on the nodes, it can be much trickier to find out, to uncover network structure. Now, what are the implications of this? Well, so it turns out that there is a notion, thinking of the matrix representation I showed you on the previous slide, there is a notion that can be ascribed to the limit of a sequence of large graphs. And this yields a limit object. Limit objects are inherently useful for our mathematical understanding because they allow us to talk about a sequence of larger and larger objects getting close to some limit, right? Now, it turns out that the limit object corresponding to graphs is most naturally thought of as a function that lives on the unit square. So think about a matrix. Back up further and further away from this matrix. Once you're infinitely far back, this object on the left and the function on the right will be indistinguishable, even though the one on the left is built using zeros and ones that are pixelated as black and white, exactly as the examples I showed you before. The trickiest part about this, however, is this business about not having known labels. So it's all very well and good if I understand exactly how this limit object corresponds to the nodes in my network, but in the absence of known labels, I know nothing. In other words, I observe something like the object on the left under a random permutation of its rows and columns, which is like a random relabeling of the nodes. And really, that's just a model for our own observational ignorance. I might observe only a sequence of connections without really understanding how the nodes are labeled with respect to an underlying limit object. And so in some sense, it's clear here that what you'd like to do is be able to talk about the limit object on the right as a function of the data set on the left. And this problem is made much, much harder in the absence of known labels. I'm going to tell you how it's possible to do this, and once you're able to do that, it's possible to talk about infill asymptotics like we would in time series. Time series has a given ordering, so there's never any problem there. And it's also, it also leads to questions of function approximation. So this is a little bit like histograms or kernel methods. If you have an underlying limit object that's something like a density, and you want to approximate that density from discrete samples, then you're going to have to do some smoothing, some function approximation. Okay, so that's really sort of the high-level view of what's going on. What I'm going to do in the next sort of third of the talk is dive into some technical details about how this works. And then I'll come back in the last third and we'll take a little bit of a look at some data and we'll sort of understand what it means to put some of these ideas in practice. Okay, so labels in a situation like this can really reveal structure. So let's take a very concrete example, and let's think about that weblog data that I described to you a few moments ago. This has on the order of 1,200 nodes, and if I look at the adjacency structure, and here I've used blue and white instead of black and white, but otherwise it's the same. If I look at the adjacency structure with respect to what I've shown you before, if I take the blocks of liberal and conservative weblogs in this setting, and I sort of order them in the way that the colors here go from red to blue to yellow, I will get the sort of two-block structure with a third block superimposed, and these are the nodes that would be colored yellow in this diagram. On the other hand, if I rearrange from sparsest to densest or densest to sparsest, I get something like this. And of course, if I apply a random permutation to an ordering like the one, either the one on the left or the one in the center, I get something that in which the structure is completely obscured. Okay? So, as I said before, the question really underlying this is, how do I make sense of a limit object without these labels? Or in other words, how do I talk about the metric structure of an object in a way that is invariant to how it's ordered? Okay? And so that means that we're not going to be able to use the sort of standard norms that we would expect to use in setting up a problem like this. We're going to have to work a little bit harder. So let me tell you about that. So the first thing we need are things called kernels, and these are going to give us our limit objects. Okay? So let's use mathcal W here to denote the space of bounded measurable symmetric functions. You'll see why they need to be bounded in a bit. They're going to be symmetric because we're going to be talking about these graphs where if I links to J, then J links to I. And now, forgetting about networks for the moment entirely, these things are going to live on the unit square. We can talk about their properties as operators, as integral operators, and we can talk about the norms that they imply. Okay? So I'm not going to dwell on this, but it will come back in one of the norms that we're going to use in a sort of slightly disguised format. Now, the name that the originators of some of this theory gave to these objects in this space is that of a graphon, which is a non-negative kernel that's normalized to live in the range 0, 1. And if you think about it, those pixelated drawings I was showing you before, if you imagine black to be a height of 1 over a patch of 1 over n by 1 over n, and white to be a height of 0, then it's clear that any network, if I transplant it onto the unit square, will in fact induce a particular graphon, a mosaic, right? Of 1s and 0s, of patches of area n 1 over n squared, of size 1 over n by 1 over n, right? So it's pretty clear that that any empirical network object induces a graphon, and indeed we're going to show later that the entire space of graph limit objects is captured by this notion, up modulo some quotient thing that has to happen in order that we take care of these invariances I spoke about a minute ago. So graphons define a generative model for graphs, for random graphs. Given the graphon object, right, and a scale, if I'd like to sort of scale down the probability of an edge, I can do that with a sequence of scales. I generate n worth of IID uniform variates. So I draw a bunch of independent, uniformly distributed random numbers between 0 and 1. And I basically take this function that lives on the square, this graphon, and I kind of query it at every pair of points. So every n choose 2 unordered pair of points here will define something in the unit square. I look into that set of points. The graphon will have a value, and then I connect vertices with probability corresponding to that value, right? So that becomes the success probability of a Bernoulli random variable. Okay? So I've kind of told you this is a sort of forward simulation question, like, okay, given a function of this type, it's pretty clear that I can generate a graph, or indeed a sequence of graphs, and I can let n go to infinity. What I haven't told you yet is, as n goes to infinity, is the object that I've generated related in any way to the underlying graphon? That's one question. And the second question is, okay, if you throw away the forward generating mechanism and you only give me the data, can I work my way backwards and solve the inverse problem as to the limit object that generated the data that I saw? So this question, as far as I've been able to work out, was first posed by a probabilist named David Aldous in 1985 in the context of something called exchangeability, which I'll talk a little bit about later. But it's really a notion of probabilistic symmetry. If you've ever thought about de Phonetic Theorem and exchangeable sequences, or if you've thought about sampling with versus without replacement, then you've bumped into exchangeability before. So Kallenberg, another well-known probabilist, was the first person to address this question, and he showed that indeed, in some sense, the mosaic, or the empirical graphon that's induced by the data that you generate, will in fact relate back to the underlying limit object. And that sounds intuitively obvious, but it still was rather tricky to prove. What I'm going to talk about in the remainder of this talk is how to actually answer this question in the affirmative and how to do it in a stronger way that involves some various degrees of regularization. And all of us in statistical modeling will know that regularization is a useful tool. It allows us to lower the degrees of freedom of our models, make them simpler, and also trade off bias versus variance in the properties of our estimators. So, how are we going to relate the empirical object, the graph that we see, to the graphon from whence it came? Okay. So to do that, we're going to have to talk about structural similarity. A type of similarity, I don't mean this in a technical way, I mean intuitively, some kind of similarity that doesn't care about the ordering of the nodes in a network relative to the limit object. So remember, we've got a function that lives on the square, and then we've got the sort of matrix of zeros and ones, and how can we understand how they relate to each other? So a simpler way to start is just to take two different networks, let's assume that they're the same size, and again ask, if we don't even know whether the net set of nodes is the same, how can we understand whether the structure of these two networks is similar in any way? So I'm going to introduce something called the cut norm, which comes from the idea of taking a graph and two subsets of its nodes and looking at the number of edges that connect the two subsets. Okay? So the cut norm then tells you something about the maximum edge set that can be obtained, and here I've scaled it by n squared so that it's nice and normalized, by looking at all s and t in the graph. So I find the two sets of nodes, and I could make them non-overlapping and mutually exclusive. It turns out not to matter except up to a constants. But I think about the two sets of nodes in the graph such that the number of edges connecting the nodes in the two sets is maximal. So that's like the densest block in the graph in some sense. And here I've normalized by n squared, but I still would favor, of course, in this case, in larger s's and t's. Right? So this kind of suggests that I can define, any norm induces a metric, so I can define a corresponding distance between two graphs, g and g hat, that happen to be on the same number of nodes. And that comes then from maximizing over s and t, just as before now, the difference, the magnitude of the difference between the corresponding edge sets s and t in the two graphs. So I'm making a very clear correspondence here between sets of nodes in graph G and sets of nodes in graph G hat. And I'm doing it by computing the edge sets over the same sets in each case, right? So now, of course, what am I supposed to do if G and G hat don't have any labels? Like, what if I don't know how to sort of compare G and G hat fairly? Or suppose that I know that the order of G hat is reversed relative to the order of G in the labels of its nodes. Well, in general, I can now minimize this quantity over all possible vertex relabelings of one graph or of the other, right? So I've got n factorial ways that I can relabel one of these graphs. So I compute this quantity, theoretically, of course, n factorial's worth of times, and I take the minimum, right? Or eventually the infimum from doing this, okay? And that in some sense, this should remind you, a little bit of how we think about distances between sets, for example. That's kind of what's going on here in some ways. And it starts to look more complicated, but I want to kind of walk you through the way in which this is actually, if you strip away all the equations, this is a fairly intuitive thing to want to do, right? So now I can take the same thing that we talked about with respect to graphs, and I can apply it to these square functions, or these functions living on the square, these things that we call kernels. The question then is, what is the analog of relabeling vertices in the graph when you have the unit interval? You have a function that lives on the square. If it were a matrix, you would relabel the rows and columns, but what are you supposed to do with a function? So instead of the symmetric group, which is the group of permutations of n objects, we have the group of measure preserving transformations. So that's basically, intuitively, the way to think about this is you chop up the unit interval into infinitesimals, and then you freely rearrange the infinitesimals at will. right? One has to be a tiny bit more careful because it's not as sort of simple as taking limits on that argument, but it should help convey the intuition that if I have a function that lives on the unit square and I want to scramble its ordering with respect to the axes, I divide up each axis into infinitely many infinitesimals, and then I rearrange them at will. And the set of all of those rearrangements will correspond in the limit to this group of measure-preserving transformations, bijective transformations that map the unit interval to itself, right? So we talked about how to look at the cut distance between two labeled graphs, so I can think about the same thing applied to kernels. And now I've gone ahead and I've gone from the labeled setting to the unlabeled setting by taking the infimum over all possible rearrangements of the ordering of one of the two kernels, right? So if I look just at the integral here, I'm taking the supremum over two sets of the magnitude of the distance between w and w hat, and then I've added in this extra step that says we look at all possible ways that we can rearrange w and w hat to make them like each other or different from each other, and then we take the infimum over all possible rearrangements. So the fact that I'm taking the infimum says that we try to make w and w hat as alike as possible in ordering before we compute. So, now, this all might feel like it has nothing to do with anything in real life, but it all links back to what I told you before, which is that when we observe a graph in practice, we rarely have all of the information that we could have about the nodes in the graph, the nodes in the network. Okay, so the last piece of theory here to tell you is the following. I've given you some intuitive explanation of how we might look at structural similarity in graphs and how we might compare a graph to a limit object. But what are the guarantees that any of this holds water mathematically? Well, so it turns out that by building up a space and taking two kernels with cut distance 0 and identifying them, we get the space of valid limit objects for graphs. So what I'm going to do at the end of the day is to use the fact that I can take this cut distance and I can use it to talk in a valid way about the distance between any kernel and any other graph kernel, and since every graph induces its own mosaic, I can talk about the distance between any graph and any other graph, right? And the important thing to understand is that eventually the space of these functions on the unit square, identified if they have cut distance 0, and the cut metric itself is compact. So what does that mean? That means, for example, that sequences are Cauchy. So as I start to look at the limit of a sequence of a family of graphs with n increasing, that I don't suddenly fall out of the space when I get to the limit. That the limit exists inside the space, everything behaves nicely, and we can talk in an honest-to-goodness way about estimating limit objects from observed graphs. If you change the game, right, so if you don't use the cut distance, but you just rearrange the two objects to be close, and you take the infimum over all rearrangements, then you will not have compactness. So a way to think about this is, if I generate two graphs at random with independent coin tosses, then as long as coin toss probability P and coin toss probability Q are close, the graphs that I generate are going to be structurally similar, right? In fact, if P is equal to Q, then the graphs that I generate are both coming from the same model. And in some sense, we would hope that in a structural similarity sense, they're close. However, since I don't know the labels of one graph relative to another, it turns out that I will never get any kind of closeness in this metric here. So two random graphs generated from the same model will be close in this cut metric, which is why the limit object makes sense here, but will not be close here. This is sometimes what you'd call in other contexts something like an edit distance, because it's sort of measuring, it's comparing two graphs by dinging you every time that there's an edge in one and a non-edge in another at the same location, and vice versa. And so this is more of the metric that you would want to use if you had a given graph W or a given kernel and you were trying to build an approximation W hat to it. And that's exactly what I'm going to do in the rest of the talk. I'm going to show a version of this which is for the mean integrated square error, which then implies convergence in this result. Okay, so that's the end really of the theory. I wanted to say one word very quickly about this from the point of view of probability and exchangeability. So this is all about symmetry. So when you think about a stationary random process, you're supposing a particular symmetry, and it simplifies the covariance structure, right? You're supposing that there's a distributional invariance to translation. No matter where I look along the real line, the process behaves the same. All that matters is the distance between two observations. Exchangeability is stronger. It's a distributional invariance to permutation. And now you can probably see why what I've talked about up until now is in some sense related to exchangeability. Because this distributional invariance to permutation is exactly what lets us talk about sort of models for graph structure without regard to worrying how the nodes in the graph are ordered or labeled or arranged or what have you. We simply require that the models are invariant to the ordering of the nodes. Okay? Another way to think about this is that this models our lack of information about the sort of true ordering of the nodes relative to a model. Right? So, if you think of De Finetti's theorem, it says that every infinite exchangeable in sequence in one dimension can be represented as a mixture of IID sequences, and something similar turns out to hold for exchangeable matrices. And this is non-trivial. It was a good sort of 30 years of work for people in different, previously disconnected branches of mathematics to come up with this result. And everything combines to tell us that exchangeable matrices are indeed natural models for unlabeled graphs. And the way this works, if we were to write it down, is to consider a formally infinite array and define it as being exchangeable if, for every finite permutation, the array is equal in distribution to its permuted version. Okay? So, exchangeable matrices absolutely admit a unique limit to representation, because even though this looks like it has nothing to do with what I've told you before, to every weakly exchangeable binary infinite array corresponds one and only one member of this space of graphons that I told you about in the past several slides. And that is a result that's called the All the Hoover Theorem. Aldous worked on this from a probability perspective. Hoover worked in model theory, so in logic. But at the end of the day, they kind of proved the same result. They proved it in 1979, but nobody really understood it until about 2005. So you can see that it's going to take us a little bit of time to make progress in this field. And then the combinatoricists kind of jumped in, and it all got very, very interesting in a good way. So let's go back to this idea of labels and permutations, and let's think about what we typically see in real data, which is the kind of clustering I told you about at the beginning of the talk. So here's that data set. It's a different school, but it's the same data set I told you about of self-reported friendships amongst high school students. I've taken the same data set and I've relabeled it or re-articulated its ordering in several different ways. So as promised, if you look at students by year in school, you see that self-reported friendships are higher when two students are in the same year. And of course, that's intuitively obvious. Grouping by race, we see what we've talked about before. In fact, here you see there are many fewer connections amongst the two races in this school in question. And then, of course, if I first sort of group by race and then I cluster algorithmically, I get even more interesting sort of patchwork structure. So this is a big warning to sort of be careful when you think about the notion of clusters in a graph. Is this the only way in which this network is clustered? Well, it sure seems reasonable, but then suddenly, if I had more covariate information about the nodes, I would relabel according to race and I would see something else. In this data set, I don't have geography, but I bet if I organized by geography, you would see that students that live closer together are more likely to report friendships. or students that previously went to the same feeder school are probably more likely to self-report friendships, et cetera, et cetera. So how do we interpret the notion of clusters in this setting? Probably the best way to think about this is to forget about clusters and think more like along the lines of bins in a histogram, right? So if the data are generated by this sort of more flexible, exchangeable model that I described, then what can we do? How can we summarize such a network? Well, I can do exactly what I suggested, which is to think about the limit object and try to reconstruct an inferred limit object from the observations that we have. And even though this might seem a little bit unnatural, it is very, very much akin to, and strongly analogous to, what we do whenever we build a histogram or any kind of kernel density estimate. There is an underlying limit object. We get discrete observations. We bin or cluster the observations. And from those clustered or binned observations, we eventually get something that is, wait for it, an optimal piecewise approximation to the limit object. And if you think about kernel smoothing, you'll know that what really matters here, well, how many clusters or bins do we have, and how wide are they, right? And as long as we have a number of bins, bins that are really wide are going to increase the bias, and bins that are really small are going to increase the variance. And as we trade off bias against variance, there are plenty of rules of thumb that will tell you how you need to adjust your histogram as n goes to infinity to get a convergent approximation to the underlying limit. So in 2D, for the graph setting that we're talking about, it might look like something more like this. Okay, so the simplest case of this is something else that's known in the literature. It's known amongst the physics community as the configuration model or the Rasch model. Sometimes it's called the beta model. It's also an example of a generalized linear model. So what I do is I assign each node a propensity for connection, right? So everybody gets a different propensity for connection, and then each edge is an independent Bernoulli variate according to the product of these propensities. And you can probably feel already, if you think about it, that what I'm about to write down for you is a rank 1 separable kernel. So this fits exactly into the broader framework that I described. There's a very clear separable rank 1 structure. In this setting, the degrees of the network after it's generated will tell you everything about people's propensity for connection, because guess what? The person in the network with the largest degree is, up to order statistics, going to be the person with the largest propensity for connection. Right? On the other hand, all the structure here comes via the degrees, via the marginals. So if you thought of this as a contingency table, this would be the marginals of the table. And maybe it's a bit unclear how to specify these propensities in the model. So it turns out that if you draw the propensities IID from some prior distribution G, then we get exactly back to the case I was describing before. So I'll let myself scale as well. You don't have to worry too much about this if you don't like. But the point is, if I apply the inverse CDF method to what I've done with G, I will recover the inverse CDF of G interpolated or queried by, if you like, a uniform variate, independent uniform variates. And now I am right back in the construction that I described for you at the beginning of the talk. I've got a function, which is the product of G inverse, and I've got a whole bunch of independent uniform random variates. And so lo and behold, I exactly have one of these graphon models that I was talking about before. And indeed, it turns out that if you try to work backward from the observed data, you will see that the probability that any one of the degrees in this model is equal to k scales exactly like the function g, interpolated in the right place. Okay? So that's just a roundabout way of saying I just showed you the second simplest possible graphon model, and now I can start superimposing these, right? I can go from a rank 1 separable model to something with finite rank. And as soon as I do that, then you should be thinking right away about Mercer's theorem and all these kind of things. And remember everything you learned in functional analysis, which tells you that it's easy then to extend to bounded measurable functions. And now I'm exactly back where I started I started from a purely combinatorial perspective. I taught you about distances between graphs, and now we've come right back around to where we started, right? So this is, in fact, a very simple model for random graph generation, and it's incredibly flexible because I can take any function w on the unit square that I would like, as long as it's bounded and as long as it is symmetric. Right? So what I'm going to tell you about in sort of the last bit of the talk is just how you can approximate this w from a data set. So you give me a graph, I return to you an approximation of w, and of course what I want to know is, will that approximation converge in the limit? In other words, am I able to consistently estimate w given a large sample of a graph, right? So I'm going to assume that w is a smooth function, and that's only so that I have a way to talk about rates of convergence. If w is arbitrarily measurable but nasty, then of course my estimates can converge arbitrarily slowly. If w is like super smooth and nice, then everything of course works more nicely. We get this random sample of uniforms that we never observe. That corresponds to the sort of hidden ordering of the nodes in the data. And we observe the outcome of these Bernoulli trials. And under this sort of shrinking sequence rho n, that allows us to let the probability of an edge go to 0 as n goes to infinity. That's going to turn out that as long as the networks aren't too sparse, then we can recover everything. In the limit, of course, if the networks are so sparse that we never observe any edges, then of course we can't recover anything. So it does break at some point, but the sparsity of the generated network only affects our rates of convergence until eventually everything breaks, right? So what we're going to do is we're going to take the graph that we observe and we're going to cluster its sets of nodes. And we could do this using spectral clustering. We could do this using any of your favorite clustering methods. The point is, if you're able to do this in a way that's consistent, a consistent estimation of the limit object will follow. And the way that this works is that you first condition on a fixed clustering. Okay, so I don't care how you got it, we just condition on it. And what you'll see is that all you're doing then is when you cluster, you look at the average number of connections in a cluster, all you're doing is summing Bernoulli random variables and averaging them. So this quickly becomes Gaussian, and the variance is quickly beat down. And so there's a very strong concentration property that happens here, as long as you have enough edges. If you don't have enough edges, you won't get Gaussian concentration. You will get sort of Poisson limiting behavior, and you'll be a bit stuck, actually. And in the limit, if you really don't have any edges or enough edges, then everything will converge to 0 very nicely. And you'll be left estimating the 0 object. So then you remove this conditioning and you use the fact that the concentration was so strong, so Gaussian concentration of measure is so strong that your result is preserved even when you realize that the clustering that's done at this stage is you sort of can account for the worst case behavior of the clustering, right? So even for a data-dependent choice of cluster, you're still fine. And then so that controls the variance of your estimation. So if the clusters are small, they're going to have more variability because you're averaging over fewer edges. On the other hand, if the clusters are really large, then you're going to be biased because just like with a histogram, if the bins are too fat, you're not going to catch fine detail in the underlying function. Okay, so that's basically the story without any equations, the story with equations is longer, but basically the same. So in practice, what do? You fix any similarity metric that you would like to compare whether two nodes in the graph have similar connectivity structure, and if they do, then you cluster them together, right? So apply your favorite clustering algorithm. If it were me and I had the data set we talked about before with the years in school, I would sure as heck initialize the data initialize the clustering according to years in school. But on the other hand, we saw that there were plenty of other interesting admissible clusterings, right? So the hard part, of course, so we've turned a graph approximation or limit inference problem into a clustering problem. And so the tricky part is determining the groups or the clusters. So what I've proved things for, of course, is a kind of maximum likelihood clustering. And that's, of course, not computationally feasible. It's easy to show that that problem lies in NP. But there's plenty of work in the literature on kind of relaxing that assumption. So I won't say too much more about it. At the end of the day, an easy way to do it is exactly analogously to a histogram. You fix all the group sizes or the cluster sizes or the bin sizes to be equal. You can build a little metropolis kernel to kind of swap nodes back and forth between groups. And you can do this in any way you'd like. The more that you can prove about this step, the more that you can prove about your approximation of the underlying limit object. What you will get out after you're done clustering, exactly like a histogram, is a kind of Riemann sum approximation of this function that lives on the unit square, this graphon or this generative W. So, what can we say? Well, if you look at the theory necessary to do this, you'll see that and so this is the stronger metric that I mentioned at the beginning of the talk, not the cut metric. You'll see that the error terms in convergence are affected by exactly what we'd expect. You pay a price for not knowing how to do the clustering, right? For the fact that the clustering has to be done in a data-dependent way. You pay a variance cost according to how small the cluster size is or the bandwidth is. And you pay a bias cost according to how large the bandwidth or the cluster sizes is. So it comes down to all the standard stuff, which is a bias variance trade-off and then a penalty you pay for not knowing how the nodes were labeled with respect to the original limit object. If you observed those latent variables, those uniform latent variables, you would simply reorder the network according to the latent variables, and then you would have an image and a limit, and you would just smooth the thing a little bit and everything would be great. And in fact, when we prove that this works, that's kind of the approach that we do. We go through a lot of acrobatics to understand how you can optimally reorder the nodes in the graph to line up to W. So there's no magic. There's very little at the end of the day that's truly new under the sun. And what we've done that's kind of helpful from a theoretical point of view is we've taken a newish looking problem about networks and reduced it to a classical understanding of nonparametric models, degrees of freedom, and a trade-off between bias and variance. So if you're curious about the effects on sparsity, green is good. So when the network is relatively dense, convergence happens quickly as a function of n. This is error. Error is going down. So badness is going down. Green means good. As the network is sparser and sparser, my rates of convergence are start to shift. And then you can see at some point, if the network is so sparse that I'm only getting like an asymptotic number of connections for each node, then I'm out of the Gaussian limit into the Poisson regime, and it doesn't work anymore. And that has nothing to do with the algorithm being bad. That has everything to do with concentration properties of averaging and when things become Gaussian versus when they fail to be Gaussian. When you're in a Poisson regime, the variance and the mean are on the same order, and so you can't squeeze out the variability anymore. You just can't do it. Going back to the data set that we looked at the very beginning, if I now take this data, I don't look at the labels, at who was liberal or conservative or whatever, I will end up with a Riemann sum approximation of the limit object that looks like this. This is just like the contour below here in terms of color. And unsurprisingly, this is, at a high level, this looks something like the structure that you see here, which is probably related to at least one sort of reasonably true labeling of this graph. But we didn't use just two groups to model this. We used something like 17. And so the only way that we have to express variability in this graph is through these blocks. And so you can see that there are a few small blocks that are very tightly coupled. And then there's this sort of multi-scale structure that if you step back a little bit, you start to see that there are many areas, there are many blocks where just nodes from one set and nodes from another set just don't connect to each other at all. And this, I will show you on the next slide, this tends to be highly correlated to the declared political affiliation of the bloggers. So in particular, this is the last thing I'm going to say. What I've done here is I've taken these 17 bins, and I've then gone back after the fitting, and I've looked at whether the blogs in these bins are self-identify as liberal or conservative, and lo and behold, most of the bins are entirely or strongly majority one political affiliation or another. And that's a nice post hoc way of checking that what you discover algorithmically through clustering is correlated with other ground truth information that we had about the nodes in this data set. So 19 of the 20 most influential liberal blogs identified by the collectors of the data are all assigned to one group, and 18 out of 20 are assigned to the group next to it. And that's exactly what's happening right here in the middle, where you start to see this big divide in these structures. So that's it. The kind of things to think about from an abstract point of view. Exchangeability or invariance to permutations here gives a really nice framework for making sense of networks where we don't have all the information we would like to about how the nodes in the network relate to one another. I think more generally, this is an example of something where tools from other branches of mathematics and other practical problems can feed back into statistics and give people in the field new things to think about. So when I first started this line of work, there were really no networks papers in any of the statistics journals, and now the journals are sort of fairly overwhelmed by them. So it's kind of caught on, because if you're an expert in non-parametric statistics, now suddenly you can connect what you're doing to this family of network problems. And I think the other kind of key benefit of this way of thinking about things is we can look at what people are doing in practical aspects of areas like data science. We can look at algorithms that empirically work well, and then we can sort of take a step back, and through a kind of bigger mathematical superstructure, we can understand why these algorithms perform well and when they're going to succeed and when they're going to fail. So proving new theorems about existing algorithms doesn't give you new algorithms, but it does put you on much firmer ground with regard to when you trust the results of the data analysis that you've done. So thank you very much, and I will stop there. And if we've got time, I'm of course happy to take a few questions. So thank you very much.
Time for a couple of questions.
Yeah.
In the original political graph that you were showing with the conservatives and the Democrats,
Yes.
What do the edges exactly represent?
Oh, sorry. I should have emphasized that more clearly. It's blogs that co-reference other blogs. So people are writing in the blogs, and then they're referencing other blogs. So if you look more closely at the data, what you'll see is that some of them are individuals and some of them are aggregators, and most of the blogs don't exist anymore because it was from 2004. But it's also the case that the blogs are sort of not of uniform type. You know what I mean? Like some of them might have been, some of them were actually, I guess they would be political action committees almost. But basically, independently of the type of blog, they typically make reference to other blogs. You could do this these days. You could do the same thing with Twitter data or something like that. Does that answer your question?
Yeah. Another very good question. So I don't know anything about network theory, but if you were to take a really sort of simple algorithm, how would that compare against the algorithm you have developed?
Yeah. So the algorithm, I didn't really develop an algorithm per se. I implemented the simplest thing I could think of, but there's a huge literature on exactly doing these kind of cluster algorithms for networks. So I think that the performance of clustering algorithms for networks is still fairly driven by heuristics. So some people I was kind of trying to do a brute force, implementation or something. it seemed to be fine. But on the other hand, like there are people who spend years and years like optimizing for scalability. I mean, if you have a network with 1 million nodes or something, you have to take a slightly different algorithmic approach than if you have 100 nodes. I think that in practice, the performance depends on a number of things. I guess my kind of point is I'm a little bit invariant to which algorithm you might use in practice. I'm kind of interested in understanding maybe, so my suggestion is like, okay, so any clustering algorithm, you give it a network, it will return to you a bunch of clusters. My kind of question that I'm thinking about is like, well, what do these clusters mean and what have you actually done? And it's a bit dicey for all the reasons that I've talked about. So like, one way to think of it is if my goal is to approximate the limit object, then any clustering algorithm that's good enough will eventually allow you to approximate the limit object. On the other hand, as I showed you in the very beginning, you can have multiple different clusterings of a network that all sort of make sense, whether it's year in school or race or geography or what have you. So I think to finally try to answer that question, I would just say that I think these clustering algorithms are becoming like technologies, and if I had to use one in a real world setting, I would try to look around and use the best, most recent one off the shelf. Does that make sense? Yeah. Other questions?
Yeah. One more question.
If you wanted to make inference on weight networks,
yeah.
I mean, currently this is a model on the adjacency matrix, right?
Yeah.
And I'm just wondering how whether you would be able to extend this, because like in the initial example you presented on interbank networks, for example, you sometimes observe something like if the probability that two nodes are linked is high, then very often also the edge size is
large. Yeah.
Exactly. And I was wondering whether you could have something that corresponds to your graphon in some sense to assign a weight. Also, how you would model this?
Yeah, so you can do it. I mean, it's easier if you have negative and positive weights and whatnot. Then it gets a bit nastier. But if we just think about positive weights, then there are definitely things you can do. I have other work that I didn't talk about in this talk that exactly encompasses that setting. As long as the weights behave reasonably, then you're pretty much fine. The other thing that I didn't talk about was if you have bipartite graphs or hypergraphs, and the theory is the underlying graphon theory becomes a little bit more complicated, and it looks a little bit less elegant. It's just kind of a bit more going on, but you can also handle those settings. So this is the reason I went with the binary adjacency structure here is because it's kind of the simplest to give a flavor of how the machinery works. But yeah, the machinery extends in a pretty easy way. And when you have weighted networks, you get these interesting questions between, the network is still probably sparse, but as you said, like having an edge, if you start to have weights that can grow, then you get, sort of different asymptotic trade-offs, but you can definitely do it. It's a good question.
I'm afraid I'm going to have to move things along, though. Can we just thank Patrick once again for a